Hello, my name is Alejandro Jenkins. I'm a professor of physics at the University of Costa Rica. And this semester, I'm in charge of an introductory course, Physics 2 for physics majors. And in this course, we've been covering in recent weeks linear oscillation, simple harmonic motion, resonance, harmonic waves. And the textbook assigned for this course, which is Resnick, Halliday, and Crane, brings up the collapse of the Tacoma Narrows Bridge in the state of Washington in the United States back in 1940 as an instance of resonance. And not just this book, but many other introductory physics textbooks over decades have presented the Tacoma Narrows Bridge disaster as a consequence of resonance and even as a paradigmatic example of resonance. And this is wrong. This is wrong. We've known for a while that what happened at Tacoma was not a resonance, but rather something qualitatively different, self-oscillation. And self-oscillation has been a subject of interest for me for a number of years now. Some of my research in theoretical physics has been focused on self-oscillation. And therefore, my students got an earful from me about how the book was wrong on this point. And later, in talking about this with colleagues, with other physics teachers at the university level, I realized that there was some interest in having at their disposal a clear but succinct explanation of what actually happened to the Tacoma Narrows Bridge, why it's not a resonance, and what it means that it was a self-oscillation. So I took the material that I had presented to my students a couple of weeks ago and made some adaptations, and now I'm recording this at home with the intention of later uploading it to YouTube, where it might be more widely available to people who might be interested in this subject. So over the next about approximately an hour and a half, I will cover this following topics. First, I'll briefly summarize what happened at Tacoma Narrows in the year 1940, what led to this collapse of the bridge. Then I will review some of the key concepts of resonance, not just linear force resonance, but also parametric resonance and nonlinear resonance, as they will be relevant to the rest of my discussion. And hopefully this will help clarify why the Tacoma Narrows Bridge cannot have collapsed as a result of, as a consequence of a resonance. And then I'll introduce the concept of self-oscillation, give the general definition and some examples. And the key point that I want to underline here is that in a self-oscillation, small oscillations about equilibrium are effectively anti-damped. So this causes small oscillations to grow exponentially in time until they're limited by some nonlinear damping. But this linear anti-damping, which is causing the growth of small oscillations, is always due to a feedback. So a feedback between the oscillator itself and its coupling to the external source of power that is exciting and maintaining the oscillation. And I will explain how this is qualitatively different from what we see in a resonance. And then I will talk a little bit about sea waves, about how the wind raises waves on the surface of the water. Here I must tip my hat to John McGreevy, who is a professor at the University of California at San Diego. And what happened is that maybe 12 or 13 years ago, when I first became interested in self-oscillation, I would often talk the ear of whoever happened to be around me about this and about how I had never been taught in my entire training as a physicist to think about this kind of phenomena, even though they were so important in real life. So some people had the sense to run away when I would begin ranting about this. But John heard me out, and then later he asked whether what I had said was applicable to the problem, to this question of how the wind raises waves on the surface of the water. I thought about it for a bit. It was clear that it was indeed a self-oscillation, but it was not clear to me how it worked. And then later I looked into literature on this issue, and it soon became clear to me that various very eminent physicists, including Richard Feynman, had thought about this problem and been stumped by it. But the correct explanation does exist in the literature. It can be found, but it has not been widely accepted as the correct explanation. So there's no general awareness or consensus among theoretical physicists about this problem, even though I will claim that the correct answer is known. And then finally, I'll summarize the main points that I hope I will have gotten across in this presentation. Okay, so right now, in this location of Tacoma Narrows, there are twin suspension bridges. This is a map of the region, and so this is part of the Puget Sound in Washington State. Here in this red circle is the Tacoma Narrows, so this is essentially a fjord within the Puget Sound. And the bridge that goes over this Narrows connects the city of Tacoma to Kitsap Peninsula. This is not very far from Seattle. But the bridge that we're interested in is neither of these twin bridges that are currently there. It's the predecessor. So this was a suspension bridge that was built between the years of 1938 and 1940, and it was opened to the public on the 1st of July of 1940. Even when the bridge was still being built towards the end of the construction process, workers reported that when the structure was hit by a very strong wind, it would wobble in some way. And later, when the bridge was open to the public, people who drove across it reported that if a strong wind was hitting it, they would feel this oscillating motion under the car, on the road over the span of the bridge. And they earned the bridge the nickname of Galloping Gertie. This went on for about 4 months until finally on the morning of the 7th of November of 1940, something changed. It might be connected with the snapping of one of the cables on the suspension of the bridge. And then the mode of oscillation of the bridge changed. So it went into a torsional motion, which we'll see in a video in a moment, and also with a significantly greater amplitude than anything that had been seen before. So this was this very violent twisting motion of the bridge caused it to fail. The structure failed. The road portion of the bridge broke and collapsed into the waters of the Narrows below after a few hours. One of the reasons why this disaster is so well known is that when the bridge was still operating, people were complaining that under strong winds, the bridge would gallop under their car. And I should say that strong winds are very common in the Tacoma Narrows because as a fjord, the path of the wind narrows and the wind speed goes up frequently. And the authorities hired a professor of civil engineering at the University of Washington in Seattle, Professor B.F. Farquharson, to look into this problem, to try to figure out what was going on and trying to come up with a solution. And Professor Farquharson took extensive film of the bridge. So first, when it had this gentler galloping motions, and then on the morning of the 7th of November, he got a phone call saying that the bridge had suddenly gone into this much more serious, much more violent twisting oscillation. And he traveled with his film camera to the Tacoma Narrows and proceeded to document the last hours of the bridge leading up to its collapse. And this film that Professor Farquharson took was soon used in various newsreels. This is in the days before television was a widespread thing. So the main source of visual news were newsreels that were shown before or after the movie in movie theaters. So in many newsreels, many newsreels showed some excerpts from Farquharson's film of the oscillation and collapse of the bridge. So this became very widely known to the public. If you're interested in the details of this, there are a series of technical reports that were published years later under Farquharson's supervision. But what I'm interested in mostly is the fact that for many decades, introductory physics textbooks have referred to this motion of the bridge leading up to its collapse as a consequence of resonance. And starting in the 90s, there have been some efforts to convey to physics teachers that this is not correct, that they should not refer to this as an instance of resonance. And there's this pedagogical article published in 1991 in the American Journal of Physics, which is a pedagogical journal for physics at the university level. And these authors, Bila and Scanlon, they go through various textbooks that mention this Tacoma Narrows bridge disaster as a consequence of resonance, and they explain in general terms why it's not. But the pedagogical reference that I would most like to recommend, if you're interested in this, was published in 2006, also in the American Journal of Physics, by two very distinguished theoretical physicists, Dan Green and Bill Unruh. Bill Unruh is retired now, but he was for many years a professor of physics at the University of British Columbia in Vancouver, UBC. And my understanding is that when this was published, Dan Green was an undergrad student who worked with Professor Unruh in this pedagogical article. Unruh is very well known, might say even renowned contributor to the theory of general relativity, this interesting, important phenomena of the Unruh effect and Unruh radiation, general relativity. And Dan Green went on to become to a successful career as a theoretical physicist himself. He's currently a professor at the University of California at San Diego. And this article, I will be referring to this article at various points throughout the rest of my presentation. This is freely available on the Physics Archive if you want to look at it. Okay, so let's look at a newsreel version of Farquharson's film of the Tacoma Narrows Bridge. I've taken this from Wikimedia Commons, so this is freely available, but you can find many other cuts that use various different parts of Farquharson's film online. So here, this is already the final day of the bridge. So it has already gone into this large torsional motion. So the span of the bridge is twisting around its long axis. And this effect is caused by the wind. So there's a wind that is blowing from left to right, as shown in here. So this left edge is the windward edge, and the right edge is the leeward edge. And this twisting motion has become so violent that a driver has abandoned his car and fled on foot. You can look at this video and estimate the period of the motion of the bridge. I tried this exercise. Let me pause this for a second. And I got a period of between 3 and 5 seconds, depending on precisely when I looked at it. Presumably this is also somewhat dependent on the amplitude of the oscillation because of nonlinearities. But I'm not absolutely sure that the frame rate that is shown in this video is the right frame rate at which this was recorded. But Green and Unruh give a period of 5 seconds, so which corresponds to a frequency of 0.2 hertz. And this is the number that I will be referring back to later on. Okay, so let me advance to the crash here. So now we see the bridge with an even larger torsional motion. Here you can get some appreciation for the windy conditions on the Narrows. Here it's an even larger amplitude. And here you see a person who is walking, actually he's walking away from the abandoned car. The story which I read online is that this person is actually Professor Farquharson. What happened was that the owner of the car, when he fled on foot, he left behind his dog, a cocker spaniel named Tuppy. And when Farquharson heard about this is Professor Farquharson carrying a pipe. He looks maybe a little bit upset. So when Professor Farquharson heard about this, he was an animal lover, so he went back and tried to rescue the dog, despite the significant risk of going back to the car when the bridge was behaving in this way, and it was clear that it was in great danger of breaking at any time. But when Farquharson got to the car, the dog was so terrified that it bit him in the hand, and it was not possible for him to rescue it. So I think this is why he looks a bit upset. He's walking away from the car. He has just been bitten by the dog. So after some hours of this wild rocking motion of the bridge fails structurally. The road surface breaks up and falls into the waters below. And my understanding is that the only casualty of this bridge collapse was the dog that had been left behind in the car. Okay, so this is from the textbook that we've been using, Resnick, Halliday, and Crane. This is the 5th edition from 2002. As far as I could tell, this is the most recent edition available of this book. And I've taken a screenshot of the paragraph where they talk about the Tacoma Narrows bridge. So they say that the wind blowing through the Narrows broke up into vortices. We'll return to this issue of vortices in a moment. In effect, providing small puffs that shook the bridge at a frequency that matched one of its natural frequencies. So that's what you would need for a resonance. You would need the external driving force to happen to have the same or very nearly the same frequency as a natural frequency of the motion of the oscillator. But then they try to make a distinction between the gentler rolling motion that the bridge exhibited the first 4 months when it was being used, and the much stronger, more violent torsional oscillation that was seen on the last day before the bridge collapsed. And then they add this very obscure sentence. They say that these last large torsional oscillations leading up to the collapse of the bridge were not a result of resonance, but of nonlinear effects due to particularly strong wind gusts. I think this is gobbledygook. I'm not sure what this means. And I suspect that what happened, I'm not sure, but I suspect that what happened is that the previous edition of the book simply said that the Tacoma Narrows Bridge had collapsed as the result of a resonance. And then somebody wrote to the author saying that was not so simple, that there were nonlinear effects at work and so on. So they added this obscure phrase, which I don't think really clarifies or helps in any way. And this is the image that accompanies this discussion in the book. And in the caption, it says that immediately after the bridge was opened in July of 1940, it showed gentle rolling oscillations due to resonance. But I think this is hogwash. Nothing here is right. The oscillation of the bridge was not due to resonance, as we'll see, was a self-oscillation. And this discussion of nonlinear effects is just confusing things further. So at least I hope that I convey to my students the lesson that in science you cannot accept anything on authority, even if it's something that is said in the textbook that has been assigned for an introductory physics course. Okay, so let me quickly review some key concepts of resonance that will be relevant to the rest of my discussion. So in any introductory course on this subject, when we bring up resonance, what we do is we take the equation of motion for a simple harmonic oscillator, and we add to it a driving force, a periodic driving force. So here the angular frequency of the periodic driving force is omega sub d, and the amplitude is f sub 0. The displacement of the oscillator is represented by the letter q, so q as a function of time has this form. This is the steady part of the solution. So in any course, we'd show that the general solution to the driven simple harmonic oscillator has 2 parts. So there's a part that moves with the natural frequency of the oscillator, the frequency that it would have on its own without driving. And then there's a part that moves with the external driving frequency omega sub d. But the first part, if there's any damping, dies out over time. So if you wait for a while, what's left is just the steady part that moves with the same frequency as the driving term, and it has a fixed amplitude A. But there's a phase shift, phi, so there's a phase difference between the driving force and the response of the oscillator. And this was a homework exercise for my students a couple of weeks ago to compute the net amount of work that this external driving force does over a full period of the motion of the oscillator. You can get the net work by integrating the power over a full period. And the power is force times velocity. So velocity here is represented by q dot. So the dot in Newton's notation represents the derivative with respect to time. And with a bit of elementary calculus, you can get that this net amount of work is pi times the amplitude A of the oscillation times the amplitude F sub 0 of the driving force times the sine of the phase phi. And then in resonance, which happens when the external driving frequency matches exactly or very nearly the natural frequency of the oscillator, this angle phi becomes 90 degrees. So sine of phi takes its maximum possible value of 1. So this is when the external driving force most effectively does work on a full period of the motion of the oscillator. And you can think of this in slightly different terms. Since this is a sinusoidal function, then the condition that the driving force lead the oscillator by 90 degrees is equivalent to saying that the driving force is in phase with q dot, with the velocity, the instantaneous velocity of the oscillator. So this means that in resonance, the external force is always pushing or pulling the oscillator in the same direction in which it's already moving. So it's always encouraging the oscillation rather than ever discouraging it. So this is why this is when it's most effective at injecting energy into the oscillation. And another thing that was also in a recent homework for my students was to use the fact that the total mechanical energy, kinetic plus potential energy of the oscillator is proportional to the amplitude squared, to show that in resonance or near resonance, if there were no dissipation, the amplitude would grow linearly with time. And this is a simple exercise. We've just used the chain rule and then set the net power E dot that is being injected by the external force equal to the net work that was computed before divided by the period. The period capital T is equal to 2 pi over omega d. And the important thing is that this network was proportional to the amplitude of the first power. And since we have an amplitude downstairs because of the square root of E, this gives me that A dot, so the time rate of change of the amplitude of the oscillation in the absence of damping, is proportional to A to the 0, to a constant. So this means that the amplitude would be growing linearly with time. And I'll distinguish this from what happens both in parametric resonance and in self-oscillation, where the work is proportional to the square of the amplitude, and therefore without damping, the A dot would be proportional to A to the first power, which means that A would be growing exponentially. So small oscillations would grow exponentially in those cases, unlike for linear resonance. Okay, so next, let me say something about parametric resonance. This is not a subject for an introductory course such as I'm teaching at the moment, but I've taught this in more advanced course on classical mechanics. So the theory of parametric resonance is based on this equation called the Hill equation. So Q double dot, again in Newton's notation, is the second derivative with respect to time of Q. So that's the acceleration of the oscillator. And if I had a constant omega squared, this would just be the equation of motion for the simple harmonic oscillator. But now I'm allowing omega to be a function of time. So this means that energy is no longer conserved. And there's a particular case of interest that is widely discussed in the literature, where I take omega squared to have this form. So it varies around an average value of omega sub 0 squared, and it varies sinusoidally with an angular frequency little gamma and an amplitude little a times omega sub 0 squared. And this particular case of the Hill equation is called the Mathieu equation. So that's the math. How would I implement this physically? So I need a simple harmonic oscillator where the natural frequency varies with time. So one easy way of doing this is to take a pendulum, because in a pendulum, small oscillations obey the equation of simple harmonic motion. But now, the frequency of the pendulum depends on its length. But now I'm going to make the length variable. So omega squared is acceleration, gravitational acceleration g divided by L. So L is a function of time omega squared becomes a function of time. And this is how you can do this. You can take a mass m and connect it to a string, pass the string, thread the string through a small hole in a vertical plate, in a solid vertical plate, and then attach the other end of the string to a point on the rim of a wheel of radius r sub 0. And this wheel will be turned by a motor. So when this point on the edge of the wheel is going up, the length L of the pendulum will be decreasing. And when this point is going down, the length L of the pendulum will be increasing. So what is the condition where the motor is being able to deliver power most effectively to the oscillation of the pendulum? All right, so it's easy to show for the simple pendulum with fixed L that the tension T of the string behaves in this way. So theta is the angle that the string makes with the vertical, and theta dot is the instantaneous angular velocity of the motion of the pendulum. And let me write theta as a function of time in this way. So it has an amplitude omega 0 and a angular frequency an amplitude theta sub 0 and a little and a angular frequency little omega sub 0. And it turns out it's easy to find that the tension and the simple pendulum oscillates in this way. So it actually oscillates with frequency twice omega sub 0, with twice the frequency of the motion of the pendulum. This is not a mystery. This is a consequence of geometry, of the reflection symmetry of the system. So whatever is happening on the left hand, on the left half of the swing must be the same as what's happening on the right hand, on the right half of the swing. And in particular, right, when is the tension maximum? The tension is maximum when the bob of the pendulum is passing through the lowest point of its swing, because there its speed is greatest, and therefore the centripetal force that the string has to exert on the mass to keep it from flying away is greatest. And there's two such points in a single swing of the pendulum. So it will pass through that point once as it moves from right to left, and then again as it moves from left to right. So there are two maxima of the tension of the string in a single period of the motion of the pendulum. Another way of saying the same thing is that that the tension is behaving in the same way, is oscillating in the same way on the left half of the swing as on the right half of the swing. So this is where this factor of 2 comes from. And now, what do I want for the action of the motor to stimulate the motion of the pendulum most effectively? I want the string to pull up on the weight when it's already going up, and I want it to slacken the string when it's going down. So I want L dot, which behaves in this way, to vary in phase with the tension. So again, very similar argument to what I said for the linear resonance. The power is tension times L dot, because the tension always points in the direction of the string. And I want this power to be always positive. That's when I would have the strongest resonance. So for this, I want the angular velocity, little gamma of the wheel, to match this frequency 2 omega 0 of the the oscillation of the tension for the free pendulum. And you can do the math, and in this situation, the net amount of work that the motor does on the pendulum is proportional to the amplitude theta sub 0 squared of the angular motion of the pendulum. So for the reasons that I said before, this implies that in this, which is the first and strongest of the parametric resonances, the amplitude of the motion of the pendulum, if there's no damping, is growing exponentially with time. But again, the point is there is a condition on the external driving force, on the frequency of the external driving force, such that it is being able to give a net amount of energy over a full period of the motion of the pendulum. And there has to be a matching of these frequencies. So there were some words about nonlinearity in Resnick, which I criticized. But it's true that nonlinear oscillators have qualitatively different features from linear oscillators. And there's two main reasons for that. So in the equation of motion for a nonlinear oscillator, there will be terms that go like q squared or q dot squared or q times q dot or even higher powers. So if you put in a trial function that moves with a certain frequency, so q of t moving with a certain frequency, say q of t going as cosine of omega t, then when you put the trial function into those nonlinear terms, you get, because of this mathematical identity, you get terms that move with different frequencies. So for instance, if I put in a trial function that moves with frequency omega, I will get from this a term that moves with 2 omega, and then a constant term. So maybe the term that moves with 2 omega, it can resonate with the linear part of the equation. And then, right, if you put in trial functions with different frequencies, you get other combination terms. So this leads to this phenomenon of harmonics and subharmonics, where in a nonlinear resonance, it can be that the motion of the resonator has a frequency that is twice as high as the external driving frequency, or 3 times as high. And also you can get subharmonics. So those are usually weaker, but you can also get a response from the resonant response at an integer submultiple of the external driving frequency. And the other important thing about nonlinearity is that it makes the frequency, the natural frequency of the oscillator, depend on the amplitude. And this can lead to a phenomenon of hysteresis. I won't get into this, but I learned about this from the first volume of the course in theoretical physics by Landau and Lifshitz, the volume on mechanics. It's a very nice but very succinct discussion of this subject. There might be other sources where this is discussed in greater length and maybe more pedagogically. But in any case, the point is that even though in a nonlinear resonator, the frequency of the motion of the oscillator might not be the same as the driving frequency, the ratio of the driving frequency to the frequency of the oscillator will be some rational number, very close to a rational number, p over q, where p and q are small positive integers. So they might be 1 or 2 or 3, but not much higher than that, because as you go up in those integers, the resonance becomes weaker and weaker. But so there still has to be a matching of the external frequency, the external driving frequency, to the natural frequency of the oscillator. It's just that the matching might not be a direct one. It might be via some low-order rational number. So here's my question to Resnick and company. Awkward question, so I'm going to phrase it using a popular meme. So here the angry goose is asking Resnick and company, with what external frequency was the bridge resonating? So as I've said, evidently the source of power that excites and maintains the motion of the bridge is the wind. But the wind on its own is not a periodic thing, it's a steady thing. And moreover, we saw from the video that the motion of the bridge had a period of about 5 seconds. So we're being asked to believe that there was something in the wind that happened to have a frequency of 5 seconds or some low-order rational multiple of 5 seconds. And moreover, that this was the case not just on this last few hours before the collapse, but over the 4 months whenever the bridge was hit by a strong wind, it would go into this large oscillations. This is just not reasonable. Okay, but some savvier people might invoke the phenomenon of vortex shedding. You can easily find discussions of this on the internet. So let me go into that. So here I've taken an animation from Wikipedia. So what's being represented here is there's a flow. The flow is from left to right, and this flow is hitting a solid obstacle here represented by this little white circle. So you can think of this obstacle as a cylinder, and the flow is perpendicular to the axis of the cylinder. And what's shown here on the screen is a cross-section of the flow. So behind the obstacle, vortices begin to form in the flow. And first, the vortex is formed on the upper half, and then it separates from the obstacle. And then a vortex forms in the lower half, and it also separates from the flow. So you get this, it's actually called the von Karman street of vortices behind the obstacle. This is a self-oscillation, and it's also an interesting problem theoretically. I don't believe that this is totally well understood theoretically. I also think it's closely connected to the problem of aerodynamic lift, which is also not totally well understood theoretically, but that's a subject for another time. Here, let me just say that the frequency with which these vortices are made in the flow is well known, can be easily measured experimentally, and it obeys this law called the Struhel frequency. So 0.2 is a dimensionless number. So there's a dimensionless number that depends on the fluid, and here 0.2 is for the air at standard pressure and temperature. And then that gets multiplied by the speed v of the flow and divided by the effective diameter d of the solid obstacle that's in the middle of the flow. Okay, so in the case of the Tacoma Bridge, we know that the wind speed was about 68 kilometers per hour in this last phase of the oscillation before collapse. And I've said that the frequency is about 0.2 hertz. So if we're asked to believe that the bridge was resonating with this frequency, then we need the effective diameter of the solid obstacle to be about 20 meters. But this is wrong. This is clearly wrong by at least an order of magnitude, because the obstacle in the flow is the side, the edge of the bridge that is facing the wind, and that might be a meter thick or 2 meters thick, but definitely not 20 meters. So there's definitely something wrong. But moreover, you'll notice that if this were really the explanation, if the bridge were resonating with this vortex shedding, then you would only see resonance when the wind speed happened to take the right value for this Struhel frequency to match a natural frequency of the motion of the bridge. And it's unbelievable that this would have happened repeatedly over 4 months, and on the final day that you would always get the right wind speed to drive this resonantly. And Green and Unruh in their article, they stress that the Tacoma Narrows bridge actually started to behave like a wind instrument. So in a wind musical instrument, like a clarinet or a flute, you have to blow into it. That's the source of power that excites and maintains the musical note. And you have to blow with a certain minimum speed. If you blow too slowly, then the note does not play. But if you reach that critical speed where the note begins to play, then if you keep increasing the wind speed, you don't change the frequency, you don't change the note. You play the same note, just more loudly. So this behavior is definitely not explainable as resonance with this Struhel frequency. There's something else going on. There's something else is self-oscillation. So let me define that. And let me give you an example, which is, in fact, closely analogous to what was happening in the bridge. So this is a video from the slow-mo guys. I'm going to show you an excerpt. I just checked, and this video currently it's 9 years old, and it has more than 20 million views. So many people have seen this. What they're doing is that they've put an old CD on a motor, and it's being spun by the motor from a vacuum cleaner. And if they spin the disk fast enough, then it finally explodes. There's a critical rotational speed of about 23,000 revolutions per minute. If you exceed that, then the CD breaks up. And here they're looking at this in slow motion. And they've drawn a happy face on the CD, and then they remark. So the happy face is spinning with the velocity of the motor, and then you'll see this traveling wave going around the edge of the CD, and they point out that this warping, so this wave, is moving through the happy face on the disk. So what this means is that the disk is actually, the velocity at which this is spinning is faster than the velocity with which this wave propagates along the boundary of the disk. And we'll return to this condition more than once. But anyway, so the point here is that this wavy motion on the side of the CD is being excited by something that doesn't have a corresponding frequency. It's being excited by the air around it as the disk moves with respect to the air. And this makes this oscillation keep growing until finally it's so great that the amplitude is so great that the disk breaks up. So this is very spectacular, and it's closely analogous to things that we'll see repeatedly in the rest of this talk. So this is a self-oscillation. What is a self-oscillation? So the canonical definition of self-oscillation is a self-oscillator generates and maintains periodic motion at the expense of a source of power with no corresponding periodicity. So this is unlike resonance. It works because there's a positive feedback between the oscillator and the modulation of the coupling of that oscillator to the external source of power from which it's getting the energy to excite and maintain that oscillation. So the oscillation itself is inducing the right periodicity in the external source of power in order to extract a net positive amount of work over a full period of the oscillation. And this is different from resonance. It's different because in any resonance, not just in linear resonance, but in parametric resonance or in nonlinear resonance, you have an external driving term, and you calculate how the oscillator responds to that external driving. But the oscillator doesn't do anything to the external driving term. So causality runs in only one direction. But in a self-oscillator, there's causality in both directions. So the external source of power acts on the oscillator, but the oscillator does something to the external source of power. It modulates the coupling of the external source of power to the oscillator in such a way that it induces the right periodicity to extract net positive work over a full period. If you're interested in this, I should warn you that the term that I'm using, self-oscillation, is not universal. So other sources talk about maintained, sustained, self-excited, self-induced, spontaneous, autonomous oscillation. In electronics, people talk about parasitic oscillations. These are electronic self-oscillations that are unwanted. In mechanical engineering, there's an interesting phenomenon called hunting oscillation. So for instance, if a railway car is traveling above a certain critical velocity, it will begin to move from side to side, to oscillate from side to side. This is called a hunting oscillation. And this can derail the car. In fact, the main challenge in building high-speed railways is having a very high critical velocity for hunting. The term that I'm using, self-oscillation, is due to Soviet mathematical physicist from the 20th century, Alexander Andronov. Sometimes it's also translated as auto-oscillation. And you can find this definition in a textbook by Andronov, Witt, and Akin. It's available in an English edition from the 1960s. But this would not be my first recommendation if you're interested in learning about the subject. My first recommendation would be this review article that I published more than 10 years ago now in Physics Reports. The title is just Self-Oscillation. It's freely available online on the Physics Archive. And what's the distinguishing feature of my treatment of the subject as compared to others that you might find in the literature? I've been, and this is something that I've been trying to continue over the last decade or so, I really advocate what we might call a physical or a dynamical approach to understanding self-oscillation. And what you can mostly find in the literature, including the work of Andronov and collaborators, is a largely mathematical or kinematical approach. So it's an exercise in the theory of ordinary differential equations or the mathematical theory of dynamical systems. Sometimes it's phrased in terms of control theory. But I really want to look into the physics of this and ultimately into the thermodynamics. Okay, so I want to get to the explanation of what actually happened in Tacoma Narrows and how it is like this shattering of the CD from the slow-mo guys that we saw a moment ago. And if there's a self-oscillation, then there has to be a feedback between the oscillator and a modulation in this external source of power for that oscillation. But it's easier, more pedagogical, I think, for me to explain this in terms of another self-oscillation of a bridge that is also well documented on video first, before I go back to Tacoma. And this instance is what happened in the Millennium Footbridge in the city of London. So this is a pedestrian bridge that was built over the River Thames, right in front of St. Paul's Cathedral. So St. Paul's is on one side, and the other side is the Tate Gallery. If you go as a tourist to London, this is one of the sites that you might visit. And when this was opened, I'm not sure if it was in 1999 or in the year 2000, the bridge soon went into this large lateral oscillation. So, and there's video of this. I got this from YouTube. And you can see in this video that the bridge is moving, is wobbling from side to side. And some people are so scared by this that they've stopped walking and they're holding on to the railing. And if you look at the people who are walking forward, you will see that they're actually not walking straight, altogether straight. They're actually swaying from side to side in unison. And evidently, it is this, let me stop this for a moment. It is this lateral swaying of the pedestrians and the synchronous swaying of the pedestrians that is feeding energy into the lateral motion of the bridge. But then the question is, why would the pedestrians suddenly all decide to move sideways in unison so as to drive this motion of the bridge? And here in this long shot, I think it's quite clear that there's this synchronized lateral left-right motion of the pedestrians who are actually walking. If this is not too clear in this video because of the recording on Zoom, then I encourage you to follow this link or just look for Millennium Footbridge on YouTube, and you'll see this more clearly. Okay, but so what's going on here is it's a feedback. So it's a feedback between what and what. It's a feedback between the lateral motion of the bridge and the lateral motion of the pedestrians as they're walking forward. So it's clear that if the pedestrians, for any reason, decided to synchronously move left to right with the right frequency, they would excite this motion of the bridge. But how is the motion of the bridge affecting the pedestrians? So this other direction of causality, in this case, it's actually psychological. So if I'm walking down the bridge and I'm trying to stay on a straight line, and all of a sudden, for whatever reason, the ground under my feet suddenly begins moving towards my left, so towards my right, then instinctively I will try to stay on a straight line with respect to my surroundings. So I will step towards my left in order to compensate for this shifting of the ground. And as I do that, my feet push the ground, push the surface of the bridge towards the right, so towards the direction in which it was already moving. And then in the next phase of the motion, if the ground under my feet moves towards my left, then I instinctively step towards the right in order to try to stay in a straight line. And as I do this, my feet push the surface of the bridge towards the left. So this instinctive response of the pedestrians feeds energy into the motion of the bridge. So there can be a positive feedback between the bridge and the pedestrians. Okay, so that was the Millennium Footbridge. What happened in the case of the Tacoma Narrows Bridge? Where's the feedback? So here the feedback is between this twisting motion of the span of the bridge. So here's the cross section, and something that's happening in the wind. So I've taken this figure from Green and Unrose article. So here the wind is shown blowing from left to right. So this is the left or windward edge of the bridge, and this is the right or leeward edge of the bridge. So as the windward edge moves up in this twisting motion, it makes a vortex in the wind, a vortex on the upper side of the bridge. And then as this windward edge moves down, it makes a vortex on the downward side of the bridge. These vortices are regions of lower pressure, and they're dragged from left to right by the wind. And under certain conditions, the pressure oscillation associated with the motion of these vortices across the span of the bridge can do net positive work over a full period of this motion. And in that case, then the vortices, which are made by the motion of the bridge, in turn encourage that motion. So that's the positive feedback. And interestingly, we can compute what that condition is for this work to be positive. There's a critical wind speed. So if the wind speed is too low, then these vortices do negative work on the oscillation of the bridge. There's a critical speed at which the work becomes zero. And then above that critical speed, the work done by the vortices is positive. And it's positive because the vortex on top pulls up on average, it pulls up on the surface of the bridge when that part of the surface is already going up. So it's stimulating that motion. And on average over a full period, the vortex below is pulling down on the surface of the bridge. It's pulling down on the bridge when it's already going down. So that also does positive work. And that condition, that critical condition, is that the wind speed must be greater than the wind speed needed to drag the vortex from the windward left edge to the leeward right edge in less than half the period of this twisting motion. So this should also remind you of what we saw in the slow-mo guy's video, where the wave around the CD was growing because the disk was spinning faster than the phase velocity with which that wave moved around the edge of the disk. And this is also similar, this is a point that Green and Unruh stressed, to how a wind instrument works. So there's a critical speed. If you blow more slowly than that, you don't excite the note. But if you blow faster than that, you excite the note. And after I talked about this a couple of weeks ago, one of my colleagues at the University of Costa Rica, he became interested and started doing some Googling. And then he found some interesting sources, which he emailed to me. And this is one of them. So this is an animation from this source. I think you can also find this on TikTok. And there's also some nice information here about what happened at Tacoma Narrows in 1940 and how this was fixed when the bridge was rebuilt later on. But in this animation, you can see this production of vortices. So this is the windward edge on the left. So when it's going up, it makes this vortex on the upper side of the bridge. And then when it's going down, like in here, it makes this vortex on the lower side of the bridge. And as shown in this animation, the wind is dragging the vortex from the left edge all the way to the right edge in a little bit less time than it takes for half the period of this twisting motion. And so this is in the supercritical regime, where the vortices do positive work over a full cycle of the motion of the bridge. Okay, so that's it for Tacoma Narrows. I wanted in the next 15 minutes or so to say something more generally about self-oscillation, why I think it's an important subject, an interesting subject, that's almost entirely outside of the scope of physics education at the university level. And let me begin with Hertz. So Heinrich Hertz is a famous German experimental physicist, so famous that the standard unit of frequency is called Hertz nowadays. So what made him so famous? Basically, he discovered, initially by accident, a way of making fast electrical oscillations. And I'll say in a moment what I mean by fast. Hertz was able to show that this electrical oscillations made waves, so electromagnetic waves, which travel at the speed of light. So this finally convinced people that the phenomenon of light was part of the electromagnetic spectrum, which is described by Maxwell's equations. So okay, so the point is Hertz had to make fast electrical oscillations, but what source of electricity did he have at the time? Batteries. And batteries make DC, they make constant voltage. So how do you take a bunch of batteries and make a fast electrical oscillation? So let me say how fast. The point is that in order to study this electromagnetic waves in the lab, the wavelength had to be of human size, so something that Hertz could probe with his apparatus in the lab. And nowadays, thanks largely to Hertz, we know that these waves travel at the speed of light, which is 3 times 10 to the 8 meters per second. So if I want a wavelength of a meter, then I need a frequency of the order of 10 to the 8 hertz. So that is 100 million cycles per second. And how do I get that when all I have are batteries that make a constant voltage? So Hertz used a spark gap generator. So he had found out that when he got an electrical arc, so a spark discharge, that this could excite another spark on a ring that happened to have the right size. But so this led him to build this spark gap transmitter. So what you have here are two conducting ends separated by a small a gap of air. And if you apply sufficiently high voltage, it begins arcing. So it begins making sparks across the gap. And that makes a fast oscillation. And you can control the frequency of the oscillation by connecting the spark gap to a resonant electrical circuit with a inductance L and a capacitance C, such that the resonant frequency is 1 over the square root of L times C. And this is a problem of what I would call DC to AC. So I've taken the name of the rock band and inverted the order of the letters, because AC DC rectifying an oscillating signal, electrical signal, is quite simple and trivial. But here we want to start out with DC. We want to start with a bunch of batteries or DC voltage and make an oscillation, an electrical oscillation with a frequency of the order of hundreds of millions of cycles per second. So this is what Hertz did. And later, shortly afterwards, Marconi used also a similar spark gap transmitter to create the first radio transmissions. Nowadays, this kind of frequencies of electromagnetic waves are called radio waves. What Marconi built was originally called a wireless telegraph. At the time, what was being transmitted was not ordinary sound, but not ordinary voice, but rather signals in Morse code. Now the spark gap is quite obsolete. It's been replaced by other methods of making electrical oscillations. But I would say that the theoretical details of how the spark gap works as an electrical self-oscillator are still not completely well understood. Of course, most people don't care now because this is such an obsolete technology. But in general, if you are interested in this problem of how to make an oscillation, how to make a frequency if you don't have a corresponding frequency to work with in the first place, then you have to think about self-oscillation. And to the extent that there's any discussion of self-oscillation in physics textbooks, you will find this in the chapter on nonlinear oscillations and some more advanced textbook on classical physics. And this discussion will be based on the Rayleigh and the van der Pol equations. So here, this goes back to the work of Lord Rayleigh in the late 19th century. So when Rayleigh was working on the second edition of his textbook on the theory of sound, he wanted to include some treatment of what he called maintained vibration. So this is his term for what I've been calling self-oscillation, such as how a clarinet works. And what he did was he took the equation for simple harmonic motion, which would be just this first and last term, and he added two terms to it. So he added a linear anti-damping term, so a term that's minus some positive number times the velocity q dot. You can think of this in terms of the power that this force is conveying to the oscillator. So power is velocity times force. So the force is proportional to the velocity, then the power is proportional to the velocity squared. And because I've chosen a negative coefficient here, then this does the opposite of what damping ordinarily does. So damping is always removing energy from the oscillator. So this term is always injecting energy into the oscillator as long as the velocity is not zero. So this causes small oscillations to start to grow exponentially in amplitude. And of course, they don't grow forever. So there has to be something limiting them. So Rayleigh added this nonlinear damping term that's proportional to the cube of the velocity. So therefore, the corresponding power is q dot squared. So this is also positive definite. So this term is always removing energy from the oscillator. So what happens is that if you're initially in equilibrium at q equals 0, q dot equals 0, then nothing happens. But that's an unstable equilibrium. If there's any small perturbation, then the linear anti-damping term will cause that perturbation to grow exponentially over time. Initially, if the amplitude is small enough, you can neglect the nonlinear term compared to the linear anti-damping. But as the amplitude grows more and more, the nonlinear damping term becomes more and more important. And finally, you reach a steady amplitude where average through a whole period of the oscillation, the energy that is injected into the oscillation by the linear anti-damping term is matched by the energy that's removed by the nonlinear damping term. And then you get a steady limiting amplitude. And this, in textbooks, it's actually usually more popular to frame this discussion using the van der Pol equation. So the van der Pol equation also has a linear anti-damping term and a nonlinear damping term. It's just that the nonlinear damping term is not velocity cubed. It's velocity times displacement squared. But you can see immediately that power is also positive definite in this case. And in fact, you can get the van der Pol equation from the Rayleigh equation by a mathematical change of variables. So they're mathematically equivalent. But what I really don't like is for the explanation to stop here, because then we have no understanding of how you can get linear anti-damping in the real world. So it would be a violation of the second law of thermodynamics for a simple fluid to actually inject energy into a macroscopic oscillation. So there has to be something going on. In nature, there are no negative frictions, there are no negative viscosities. So this is the simplest example. It's actually also of great practical importance of how you can get an effective negative damping without violating the laws of thermodynamics. So this is an electrical example. So I've taken an RLC circuit. So this has a resonant frequency. The resonant angular frequency is 1/√² of L times C, where L is the inductance and C is the capacitance. So you can imagine, say, this might be the tuner for the radio, right? Where if the frequency of the signal that goes into V in matches the resonant frequency over square root of LC, you get the most output V out. But here I'm going to do something a bit different. I'm going to take the output and give it to an amplifier, feed it into an amplifier. And the amplifier will multiply the voltage by a gain of little g, a constant gain. And then I take the output of the amplifier and I feed it back into this input V in. So V in is G times V out. And I'm going to assume that the amplifier does not take any current from the circuit. It needs current to operate, but it takes that current either from a battery or from the plug on the wall that it's hooked up to. So that's its own external source of power. And in this case, it's easy to show that the differential equation for V out has this form, and then the damping term, the term proportional to V out dot, it becomes negative if the gain factor is greater than 1. So even though you have a regular positive resistance here, because of the amplification and the feedback, it small oscillations, small electrical oscillations are anti-damped, so they start growing exponentially in time. They don't keep growing forever because the amplifier saturates. It cannot produce arbitrarily large voltages, and you can think of that saturation as the nonlinearity that limits the growth of the amplitude of the oscillation. And this is the principle on which all clocks work. So, for instance, in the quartz wristwatch, there's a quartz crystal that plays the role of the LC here, and the output of that quartz crystal is fed into an amplifier powered by a battery, and then that's fed back into the circuit, so that causes the oscillation of the crystal to be sustained, and there's a mechanism that counts the number of cycles of that oscillation in order to measure time. So let me just mention very briefly, there's another class of self-oscillators in which the period is not controlled, is not related to a linear resonance at all. The simplest case is this Pearson-Anson flasher circuit. I built this with the help of an undergrad student some years ago. I learned a bit from that exercise. So here there's no resonant frequency because there's no inductor, there's no L. There's a DC source, V0, there's a resistance and a capacitance, and then I put in parallel the capacitance a neon lamp. So initially when the voltage is low, that neon lamp is not conducting essentially any current, so it's basically like an open circuit. But as the capacitor begins charging with this exponential curve of an RC time constant, and at some point the voltage crosses the threshold for ionizing the neon inside of the lamp. I believe this was in practice for a regular neon lamp, this was something like 110 volts. So when you cross that threshold, suddenly the lamp is conducting very effectively. So it's essentially, it becomes a short. So then it discharges the capacitor very quickly. So this is this fall in the voltage. It doesn't discharge all the way to zero. This is something I learned by doing this in practice. It discharges in practice to something like 80 volts. So you get this oscillation of the voltage between 110 and 80 volts, more or less. So and then you see this regular flashing of the neon lamp, where the period of the flashing is given by this RC time constant. So this periodicity is really controlled by RC, not by a resonance. The same van der Pol that we mentioned a moment ago called this kind of self-oscillation a relaxation oscillation. There was a German guy, Friedlander, who worked on this at around the same time, who gave it a different name. He called this tipping oscillations. But this is very important in biophysics because the heart and neurons and other oscillators that we have inside of our body are relaxation oscillators. The main difference physically between a relaxation oscillator and weakly nonlinear self-oscillator like maybe the quartz watch is that this relaxation oscillation loses all of its internal energy, or almost all of its internal energy, between one period and the next. It all has to be replenished from the external source every period, whereas in a weakly nonlinear oscillation, only a small amount of the internal energy of the oscillation is lost in each period and needs to be replenished from the external source. Okay, and one place where this is important is in the electrophysiology of the heart. So some review article of that subject, I found this quote from Leonardo da Vinci in English that says, "Of the heart, it moves itself and does not stop, if not eternally." This is referring to an observation which I think dates back at least to Galen in the 3rd century AD. So Galen noted that you could take a live animal and remove the heart from it, sever all of the nerves that connected the heart to the rest of the body of the animal, and the heart would continue to beat for some time. I think maybe of the order of a minute or so, before it stopped completely because of the lack of blood flow. But that taught Galen, and this is what what Leonardo is referring to in this quote, that the periodicity of the heartbeat is not given to it by the nervous system of the animal. It's actually internally generated by the heart tissue. And the period, of course, the period of the heartbeat is variable, so it's shorter when we are excited or in exercising. It's longer when we are at rest. And it's controlled, it doesn't depend on any resonance. It depends on the magnitude of the depolarization current. So how quickly the cell membrane depolarizes in the heart cell. And the body actually controls that chemically. It controls it via the concentration of adrenaline in the heart tissue. So if there's more adrenaline in the heart tissue, this depolarization current is bigger. So the cell membrane depolarizes more quickly, and therefore the heartbeat becomes faster. I won't say much more about this because this would make for a whole nother talk. But there are models of the heartbeat such as the Fitzhugh-Nagumo model, and similar models are also applied to the firing of neurons. But again, my objection is that these models are almost entirely mathematical or almost entirely kinematic, if you want. The physics of this kind of processes is still very little studied. Okay, and in the last 15 minutes, I want to talk about C waves. So one of the reasons for this is that, as I said at the beginning, I've been teaching waves to physics students. And I remember, this caused me to remember a comment in the Feynman lectures where Feynman says that whenever one is teaching waves, one is tempted to use C waves as an example. But this turns out to be a bad idea because C waves are very bad pedagogically. He says they're the worst possible example because they're in no respects like sound and light, and they have all of the complications that waves can have. So here's a diagram that I've also taken from the Feynman lectures. One of the first things that I said about waves to students following text is that and so in a wave, the wave travels in some direction and it carries energy with it. But the elements, so let's say this is a mechanical wave, so the mass elements of the medium in which the wave is propagating, they're not being carried along by the wave. They're moving, but they're moving in place around their equilibrium position. And if the motion of the mass elements is along back and forth along the same axis of the propagation of the wave, then those are called longitudinal waves, and sound is a longitudinal wave, sound in the air. And if the motion of the elements is perpendicular to the direction of propagation of the wave, that's called a transverse wave. And light is a transverse wave. Of course, it's not a mechanical wave, it's a wave in the electric and magnetic fields, but the electric and magnetic fields vary in a direction that is perpendicular to the direction of the propagation of the wave. And it turns out that water waves, so waves on the surface of the water, are neither transverse nor longitudinal, or both, I don't know, because an element of water moves along a circle or an ellipse as the wave is passing through it. So sometimes it's moving parallel to the wave vector, and sometimes it's moving perpendicular to the wave vector. But perhaps an even more serious complication from a pedagogical point of view is that waves on the surface of the water have this highly nonlinear dispersion relation. So the relation between angular frequency omega and wave vector k. There are two different types of restoring forces that are relevant to waves on the surface of the water. One of them is gravity. It's just gravity. Gravity, of course, wants to make the surface flat again. And the other is the surface tension, here represented by the lowercase sigma. Rho, of course, is the density of the water. So surface tension also would like to make the surface flat. And the effect of gravity is dominant for long wavelengths, therefore for small values of k. And the effect of surface tension is dominant for short wavelengths, therefore for large values of k. And you can find from this the phase velocity. Here it's expressed as a function of the wavelength lambda. So lambda is 2 pi divided by k. And here in this graph, the curves, the dotted curves, so this increasing dotted curve is what would happen if you had only gravity. So this is the effect just of gravity. So gravity causes longer wavelengths to propagate with a greater phase speed. And this decreasing curve is what you would get from surface tension. So surface tension makes shorter wavelengths propagate with greater phase speed. So you have to add those two contributions, and then there's a crossover between being dominated by surface tension at short wavelengths and being dominated by gravity at long wavelengths, where you get actually a minimum of the phase velocity. And mostly I'll be interested in the rest of the discussion in this regime where the wavelength is of tens of centimeters or higher, where you're dominated by gravity. But this makes the surface of the water a highly dispersive medium for the propagation of waves. Okay, but so this is the comments that Feynman makes in the Feynman lectures. But one thing that I learned in looking into this is that there was another more interesting connection between Feynman and waves on the surface of the water. And here let me quote from a best-selling biography of Feynman by James Gleick, published in the 1990s. This is from the preface or the introduction. So Gleick says, Feynman could not or would not distinguish between the prestigious problems of elementary particle physics, such as what won him the Nobel Prize, and the apparently humbler everyday questions that seem to belong to an earlier age. No other physicist since Einstein so ecumenically accepted the challenges of all of nature's riddles. Feynman studied friction on highly polished surfaces, hoping and mostly failing to understand how friction works. This is something that I've been thinking about the last few years, but be a subject for a totally different talk. But then Gleick adds that Feynman tried to make a theory of how wind makes ocean waves grow. As he said later, we put our foot in a swamp and we pulled it up muddy. So Feynman says that he tried to tackle this problem of how the wind makes waves on the surface of the water, but was stumped by it. And I tried to look at where it was that Feynman had dealt with this, approached this problem. And it turns out that there's a PhD thesis, which Feynman directed at Caltech. This is a thesis from 1955 by somebody called Al Hibbs. And you might have heard of Hibbs because there's a well-known textbook by Feynman and Hibbs on the path integral in quantum mechanics. And Hibbs, I think he was originally, he really studied math. Then he worked for many years at JPL. And I think relatively late in life, he wanted to get a PhD in physics. So he was friends with Feynman, and Feynman saw an opportunity to try to deal with this problem. So in this thesis, Hibbs, under Feynman's supervision, he tries to explain how the wind drives the wave in terms of stochastic driving by the turbulence of the air on top of the wave. And it turns out, as Gleick quotes Feynman saying here, that this didn't work. But it turns out that the correct explanation for this problem of how the wind raises waves on the surface of the water does exist. It is available. It's just not widely recognized as such. And here I'm going to borrow something from a talk that Kip Thorne gave in 2013 at Caltech. This was for the celebration of the 60th birthday of John Preskill. And Thorne gave a talk about the history of his scientific bets. Most famous ones, of course, were with Stephen Hawking. But actually, Thorne explains that the first bet that he ever made was Soldovich, after Soldovich claimed that he had an argument for why rotating black holes should radiate. And Soldovich won this bet. And Thorne explains that this was because Soldovich knew something that Kip Thorne didn't know. And this is precisely how the wind makes waves on the surface of the water. So I've borrowed this diagram from, slightly adapted from Kip Thorne's talk. So I have here two layers of fluid, a layer of air on top of a layer of water. And then there's an interface between them. So I consider some wave, a traveling wave on that interface on the surface of the water. So little v is the phase velocity of whichever wavelength I'm considering. And the corresponding wave vector for that wavelength is k. And now, okay, so these are the articles that Soldovich published in the early 1970s. He doesn't specifically talk about air and water. And I'm almost sure that what he was actually inspired by was Landau's criterion for the critical velocity in superfluid. But the physics is essentially the same. And Seldovich does this relativistically, but because I'm going to talk specifically about air and water, and wind speeds in my experience are pretty non-relativistic, I'm going to do the same analysis, but non-relativistically. So if we're looking at small waves on the surface of the water, we can write down a linear wave equation. And if it's linear, I can use complex numbers and then extract a real part at the end. This makes the calculation simpler. But the point is that the air has some viscosity. So if the air is at rest, there must be a damping term in the linear wave equation for the water wave. So there must be a term that's proportional to the first derivative of this psi with respect to time. And now if the air is moving, so if the wind is blowing, I might look at the problem again, but now in the co-moving frame of the air, so in the frame in which the air is at rest, but the bulk of the water is moving backwards with velocity capital V. And I do the Galilean transformation, so Seldovich does the Lorentz transformation, but the only difference is a factor of gamma. It doesn't change the reasoning at all. And this transformation mixes the derivative with respect to time with the derivative with respect to the horizontal position x. And if you do a little bit of algebra, you find something quite interesting, which is that there's a critical velocity above which this damping term changes sign. So it goes from being a damping term to being an anti-damping term. And that critical condition is that the wind speed capital V be greater than the phase velocity little v of the wave mode that we're considering. So if the wind is blowing faster than the phase velocity of some wavelength, then that wavelength will be amplified by the action of the wind. And this is correct. I'm not entirely satisfied with this argument because it's still somehow kinematic, right? I would like to understand what is the feedback mechanism that is actually amplifying the wave on the surface of the water. And it has to be a feedback between the wave and the oscillation of the pressure of the air on top of the wave, which is what drives it. And I'm going now to refer to a video. This is part of a very, very great series of instructional videos on fluid dynamics made in the 1960s and 1970s. And you can easily find this online if you Google for them. So this is the video on flow instabilities, which was prepared by a guy who was a professor of aeronautical engineering at MIT, Erik Molo Christensen. And he does, I think it's a completely correct discussion of this. It's very succinct, so it's a bit too summarized. You have to do some work in order to fully absorb what he's saying. But it's I highly recommend it if you're interested in looking into this. And I've taken this screenshot from that video. So Molo Christensen is looking at the problem now in the rest frame of the wave. So the wave is stationary. And we're in this situation where the wind speed, capital V, is greater than the phase velocity of the wave, little v. So in the rest frame of the wave, this means that the wind is moving in one direction and the bulk of the water is moving in the opposite direction. If that's the case, then you'd expect that the air that is in the trough, in the valley of the wave, will be slowed down a little bit compared to the air that is blowing at or above the crest of the wave. And if it's moving more slowly at the trough of the wave, then by Bernoulli's theorem, the pressure should be higher at the trough and lower at the crest. And some sources call this effect suction. So this can indeed cause the wave to increase. This can amplify the wave because you see that the high pressure is pushing down on the trough and the low pressure is sucking up on the crest. The trouble is that for this to amplify the wave, so this is like an anti-restoring force. This is a force, the suction, unlike gravity, it tries to, it prevents the surface of the water from becoming flat again. But in order for this to amplify the wave, this suction effect has to win out over the restoring force of gravity. And you can put in the numbers. So this analysis with an ideal flow where you don't consider the viscosity of the air is called, the result is called the Kelvin-Helmholtz instability. And if you try to explain how the wind makes waves on the surface of the water in this way, you find that the numbers don't really work out. And this is done in detail in chapter 14 of this recent book by Kip Thorne and Roger Blandford, Modern Classical Physics. And they point out that if you put in the numbers for air and water, you get that in order to make a wave with a wavelength of about 10 meters, you'd need the wind speed to be about 450 kilometers per hour. And that's higher than the greatest wind ever observed in the largest hurricanes on Earth. Whereas it's not so difficult to see wavelengths of the order of 10 meters in the ocean. So something is wrong, right, with this, at least with it as an explanation of what actually happens with the air and the water. But Molo Christensen then takes the next step and arrives at what I think is the correct explanation. So you have to take into account that the air has some viscosity. And this is also what justifies this damping term that Seldovich put into his linear wave equation, and which he then transformed into the comoving frame of the air in order to get to his result. And the air's viscosity introduces a phase lag between the oscillation of the pressure of the air and the wave on the surface of the water. And because in this regime where the wind speed capital V is greater than the phase velocity of the wave little v, the wave is moving backwards with respect to the wind, with respect to the air, and therefore this this phase angle actually becomes a lead angle. So the pressure of the air, the oscillation of the pressure of the air leads the wave by an angle phi. So therefore the sine of phi is some positive number. So if you go back to the discussion of resonance that I had at the beginning, this tells us that the net amount of work that the air pressure is doing over a full period of the wave is positive. And another way of saying this, which Molo Christensen also illustrates, is that this lag introduced by the air viscosity means that the average pressure that the windward side of the wave sees is greater than the pressure than the leeward side of the wave sees. So there's a pressure difference from higher pressure on the windward side, lower pressure on the leeward side, and this pressure difference is pushing the wave along its direction of propagation. And you can also find a discussion in words of the same thing it's buried in the 6th and last edition of Sir Horace Lamb's Hydrodynamics. I looked into this, and he has a discussion of this Kelvin-Helmholtz inviscid analysis towards the beginning of the book, closer to the beginning of the book. And he points out correctly that this is not a satisfactory explanation of how the wind raises waves in the water. But then later, and this might have been added in a later edition, towards the end of the book, there's this discussion, and he says when the air is moving in the direction in which the waveform is traveling, but with a greater velocity, so this is this condition that capital V, the wind speed, be greater than little v, the phase velocity of the wave, there will evidently be an excess of pressure on the rear slopes as well as a tangential drag on the exposed crests. Hence, the tendency will be to increase the amplitude of the waves to such a point that the dissipation balances the work done by the surface forces. All right, so that's what I wanted to say about sea waves. So the explanation can be found, but eminent people have not. I should say, like, and this is kind of a mystery to me that Thorne and Blandford in their textbook, they say that this Kelvin-Helmholtz explanation doesn't work, and that therefore you need to take into account the turbulence of the air on top of the water, and that's what Feynman and Hibbs tried to do in the 1950s, and Feynman eventually concluded that this did not work. And yet somehow Kip Thorne also mentions that Seldovich did know this problem, how the wind raises waves on the surface of the water, and gave a correct argument in that talk. So I'm not exactly sure why it is that this knowledge has not penetrated more deeply into the physics community. Well, so the main points that I wanted to get across were, so I remind you of the definition of self-oscillation. So a self-oscillator generates and maintains a periodic motion at the expense of a source of power with no corresponding periodicity. This is different from forced and parametric and nonlinear resonances, because in resonance, you give yourself an external periodic driving and you compute the response of the oscillator to that periodic driving, but the oscillator doesn't do anything to the periodic driving. In the case of self-oscillator, there's always a feedback between the oscillator and the modulation of the coupling of the oscillator to the external source of power, such that the oscillator itself induces the right periodicity in the external source of power to be able to draw net positive work over a full period of the oscillation. And you can represent the effect of this, in many cases, you can represent the effect of this feedback as a linear anti-damping of small perturbations. But I'm really unhappy when the explanation ends there with the putting in a linear anti-damping term into the equation of motion, because that gives you no understanding of the physics of why this is allowed and why this is not against the laws of thermodynamics to have a negative damping. Then this anti-damping causes small oscillations to grow exponentially in time. So something must eventually limit them so that they don't keep growing forever and you reach some steady amplitude. And for that, you need to include nonlinear damping terms in your analysis. And I said something about how this works in the case of waves on the surface of the water, which is an interesting example. And you should also have connected this condition that the wind speed exceed the phase velocity of the wave with the critical condition for the Tacoma Narrows bridge, that they had to have a wind speed such that the wind drags the vortices from one edge of the bridge to the other in less than half a period of the torsional oscillation of the bridge. And also with this example from the video of the slow-mo guys of the CD being shattered when it's spun at a angular velocity greater than the angular velocity with which this wave propagates around the edge of the disk. But more generally, you have to think about this kind of approach if you're ever interested in understanding how you make a wave or how you create a periodicity without having a corresponding periodicity to work with in the first place. So this problem of DC to AC that I also mentioned in the context of the work of Hertz. So that's what I wanted to say. I've tried to give useful references in case you want any of you wanted to delve more deeply into any of the parts of the discussion. But also I'm very happy to be contacted in person if somebody is interested in this subject. Thank you very much.